Okay, so today I want to talk about an extension of the economic dispatch problem, which is it's called the DC optimal power flow problem, and DC stands for direct current, and it's basically the economic dispatch problem that we've seen already, so welfare maximization, but we throw in these transmission constraints that we saw last week. And I'm going to follow the structure of the class that we did, not last week, but 2 weeks ago, where if you remember what we did first is we solved the problem from the point of view of a system operator that knows everything. We examined the KKT conditions, discovered some of the properties of the optimal solution, and then we asked ourselves, okay, what would happen now if instead of having a centralized operator that solves everything, we are actually buying and selling power. And the main punchline from that class was that if we leave it up to market agents to trade, they will come up with the same allocation of production and consumption. And we're going to find that even if we throw transmission constraints into the network, we get the same result. So this result that we saw 2 weeks ago generalizes in the case where we have constraints on power flow. So I'm going to start first with the centralized problem. We're going to look at its KKT conditions, and we're going to look at two different formulations of the problem. So, like I mentioned a couple of slides ago, what the optimal power flow problem is the economic dispatch problem with transmission constraints. What's changed compared to the economic dispatch problem is that now we have a network of buses and transmission lines, and how we inject power in the different buses. We saw there's a linear mapping of how we decide to inject power in each location and how much power we're going to get in each line. You tell me what the power is that you inject in each location. I can tell you how much power is going to flow over each line of the network. Now, the moment you impose limits on the lines, on how much power can flow through the line, there's a chance that what you would have done in economic dispatch is now going to violate the transmission limits of the line, so we need to account for that. And there's two ways we can model this. We can either use the power transfer distribution factors, where the decision variable that we're using for modeling power flows is directly the flow on the line. I'll remind you of the formulation in a couple of slides. Or we can use the reactance of the line. So there, the decision variable that we're going to work with in our model is the bus angles. So here's the first version of the problem that we will see, and then I will show you another equivalent formulation of the problem. What's new here? It's kind of just a bunch of notation now, so I haven't explained what each of the variables is here, but these, okay, F denotes flow of power over line, and capital T is the amount of power that a line can absorb without violating its thermal. So it's basically the thermal limit of the line. So this first constraint here says you cannot, and now we are introducing flow with an index K, which indexes lines. So indirectly here, we are making an assumption about directions of lines. So what we have is really a directed graph. What K is, for example, in a 3-node network, or even just a 2-node network, you have to specify what its from node is and what its to node is. So this is a, by defining the line in the network as 1, 2, we're indirectly, arbitrarily assuming that this is a directed graph where this arc is directed from 1 to 2. So implicit here in the indices is that we have a directed graph. This f variable is not to be confused with the welfare function and the cost function. These are functions here. These are decision variables, and I maybe should change the notation in the future. So these constraints we've seen before, the maximum limit of power consumption of generators and load. And now we have the PDDFs come into the problem. And what they say is, the other variable I should define is the R subscript n. So n is indexing buses in the network, and Rn is the net amount of power that is injected in a bus. For example, in this two-node network, if we have a production of 10 megawatts and a consumption of 3 megawatts, R of 1 would be 7. It can be negative, by the way. If this were 13 megawatts, R of 1 would be minus 3. So R and as well as F are unrestricted in sign. There's nothing that imposes that they be positive, non-negative, or non-positive. So what the basically this equation is all of last lecture. The reason we bothered going through all the stuff we did last lecture is to get these linearized equations that map. You tell me what the injection is in each bus, I tell you what the flow is. But now I have to worry about whether I'm violating the limits on the lines. That's the new constraint. The reason we set this whole thing up is to make sure we don't violate these constraints here. So this equality constraint, the second to last, is basically just defining the net injection as what I described here. G subscript n is the set of generators that are located in that bus. N. So what Rn is the total production from generators located in that bus minus the total consumption from loads located in that bus, where L sub n is the set of loads located in the bus. Okay, so if I add a generator in location 2, that is not going to count towards R1. That is part of R2. And whenever you're producing, it's counting positive. If there's a load here, it's counting negative, but for R2, not for R1. And this, so if you remember from last lecture, and this is kind of a detail, but maybe you've picked it up from the homework, this is in rank n-1, where n is the capital N is the number of buses in the system. It's a rank n-1 set of linear inequalities, and then we throw in this power, this conservation of energy constraint that makes it a full rank system, that makes this mapping of injections and flows a one-to-one mapping. So the conservation of energy constraint says that if on net I'm injecting 3 megawatts here, then on net I have to be consuming 3 megawatts here. So when I add up the net injections from all buses in the network, including the hub, then the total, yes?
The constraint is equal and then nothing?
This, okay, so all of these, I'm following this notation that I was following also in the economic dispatch problem. I'm already defining dual variables for each of these constraints.
Just pk, there is, before pk, there is equal and yeah.
Oh, I'm sorry, that would be a 0. Thanks. So, yeah, I will change that. This is, see, it's, yeah, no, that's okay. I'm sure you will find many opportunities to correct my French, by the way. That's I'm taking revenge on you for the suffering that I've been going through in the French classes.
It's a bad idea to make a mistake in Greek.
But I can, it's easily confused. Okay, so here's what I just said in, about the notation. So the new things that we're seeing here compared to the economic dispatch problem is that now we have a node structure. So we have buses and lines, which we didn't have in the economic dispatch model. So we're introducing a topology basically in the network. So we have to now tell you what the network looks like and where everything's located. And the buses of the generators and the lines are used for identifying locations of things. We have a new decision variable, and I've forgotten also to add here the other new decision variable, which is the power flow on lines. And by the way, one important thing to mention here is that when we're defining this model, we have to make arbitrarily, but we have to choose which is the hub node. The reason we have to do that is, if you remember from last class, the power transfer distribution factors will depend on what we choose as the hub node. If we choose a different hub node, the capital F's here are different. So each instance of this model is implicitly assuming that we've also told you what the hub node is. And you can think of these R variables here as power that you're shipping from bus N to the hub node. So it's a net injection, but where is that net injection going? Because of the power balance constraint, it's going to the hub node. So here I could choose bus 2 as the hub node. So R1 would indicate the power I'm shipping from bus 1 to the hub. If I had chosen 1 as the hub node, R2 would indicate the power that I'm shipping from 2 to the hub. Okay, and these are the new constraints. So we have 4 new constraints here. Now, we're going to go through the same exercise. Everything okay so far? We're going to go through the same exercise of looking at KKT conditions. It starts becoming a bit more hairy, the more things we're adding into the model, but still it's clean enough to get some understanding of the fundamentals. And this is really important because 10 or 15 slides from now, I will show you a real market that uses these dual variables to run basically to price power in a few thousand locations, and you can use these KKT conditions to understand why these prices are what they are. So analyzing the KKT conditions is actually quite helpful. What I've done here is I've listed the primal feasibility constraints first, nothing no deep insight there, we just discussed them. These are the dual feasibility constraints. The left one here corresponds to the flow decision variable. So if you go through the exercise of writing out the KKT conditions, when you take the gradient with respect to the flow, the FK decision variable, you get this here. When you take the this is when you take the gradient with respect to the net injection decision variable. That's the stationarity condition. This is the stationarity condition when you take the gradient with respect to the FK, to the flow decision variable, and the rest here is the, these are the usual complementarity conditions of dual variable and primal constraint, and primal constraint stationarity condition for the non-negative decision variables. There's this pattern that if you do the KKT conditions enough times, you learn how to write these out automatically if you haven't learned that already. So we have, I'm going to focus your attention on what we did also in the economic dispatch problem. I'm going to do the same trick again. I'm going to focus your attention on these conditions and these two over here. What happens if a generator is producing above 0, below technical maximum? Use this, and you can say something. About the relationship of its marginal cost with respect to some dual variable. So what?
G equals 0.
G equals 0.
So, if G equals
So this now is activated as an equality because P is strictly positive. And now, if you remember right, we had this lambda back in the economic dispatch problem. Now the role of that system lambda is taken by this rho of that location. So N of G here is just the bus at which this generator is located. So now we used to have a global lambda. That's now replaced by this rho of a given location. It's not a lambda that's common to all the network anymore. It's a rho that's specific to a bus. Same conclusion if you do that for the loads. Basically, this part of the KKT condition set has not changed. It's the same. It's just that that lambda you used to have is replaced by this rho. So all the conclusions we made back then about the economic dispatch problem are the same. It's just that now we don't have a common lambda for all the network. We have a rho that changes from bus to bus. So this is the summary of what we can observe. If a generator is producing strictly within its operating region, its marginal fuel cost is equal to this rho. The same for loads. If they're consuming strictly within their region, their marginal benefit is equal to this rho. And if a generator is at its maximum limit, it means that it's cheap enough so that its marginal cost at the maximum production is still cheaper than this local rho. Also, if a load is consuming at its max, it wants power so much that even the marginal benefit at the maximum of its consumption is still above this threshold rho. So this rho is a threshold. You tell me what it is in a certain location, I can tell you which generators will produce and which loads will consume. The generators that are cheaper than that local rho will produce. The loads that are more desperate or eager than that local rho will consume. Is that clear? Okay, so, and the other way around. If you're not as cheap, you will not produce. If you're not as desperate, you will not consume. And that's basically the solution to the optimal power flow problem. But now, the lambda was easy to kind of see the last time. All we did is we took an increasing supply curve, a decreasing demand curve, we took their intersection. That was the best way to dispatch. Now this rho behaves it depends in complicated ways on a bunch of other stuff. So sure, it's a threshold for each bus, but how we get it is a different story. And there's a whole sensitivity analysis that you can do. Again, remember these dual multipliers, they correspond to sensitivities of the objective function when you increase stuff on the right-hand side. So what do you think? Oh, sorry. So here's an easy one to analyze in terms of sensitivity. What do you think the lambda plus represents in terms of sensitivity? If it's positive, can you say something about a line? You can think of this symbol network here. The interpretation of a dual variable in terms of sensitivity is that if you increase my right-hand side a bit, the lambda captures the increase in the objective function. So if it's positive, what can you say? What can you say about a line? Would it be possible for a line to not be congested, which means that the flow is equal to the max limit over the line, and have the lambda positive? If the f on that line was strictly below the limit of the line, would anything change? So suppose in this example here that I have the limit of power that a line can carry is 100, and the flow is 90. and I go from 100, so we're sending 90 megawatts from 1 to 2. I go from 100 to 101, and I resolve the problem. Is there any chance I'm going to get a different answer about what the optimal solution is? I'm already, even with a smaller capacity of 100, I'm already getting the optimal dispatch. So even if you increase my capacity of the line just a bit, it doesn't make a difference. I'm going to give you the same answer about how you should dispatch. So there's no way that the lambda is positive if the flow is strictly less than the capacity of the line. But if the lambda is positive, now I can tell you for sure that this line is at its limit, because if lambda here is, for example, $10 per megawatt hour, I know from the sensitivity interpretation of the lambda that if you go from 100 to 101, I will have an increase in the objective function of $10 per megawatt hour. So there will be benefit. So actually, if you push me from 100 to 101, I will send more power over the line because things will change. That's why the objective function will change. So I know that when these multipliers here, lambda plus, are positive, the constraint is binding, basically. And there are similar interpretations about, well, I'm going to focus on the sensitivity interpretation of a couple more things here. One is the rho, and the other is the phi. And so the sensitivity interpretation of the phi is that how does my objective function change if I relax this constraint by relax. If I change it by slightly increasing the right hand side, how does the welfare change? Well, basically, because this is just the total, we're summing now the net injection over all buses, so this is basically the total production minus the total demand. Slightly increasing the right hand side here is basically saying that the amount of power that you're shipping to the hub minus the total consumption that you're taking from the hub, that is not equal to 0 anymore. It's equal to something slightly bigger than 0. So basically that's equivalent to asking from the network to consume a bit more at the hub. To produce a bit more at the hub or consume a bit less. So that's actually going to hurt the network. When you're asking the network to produce a bit more at a certain location, it's going to be more expensive. Or if you're asking it to consume less. So this dual interpretation of phi and rho is, you have to think about it a bit more. It's not as direct as the lambda plus and the lambda minus, but it's there if you think about it. So similarly, the rho is, if you recall what I showed you here, it's this equality constraint over here. So increasing the right-hand side a bit is like saying that I'm giving you a bit of free power at that location. The reason being that how do you get an increase in the right-hand side? You either increase the consumption a bit or you decrease the production a bit. So the sensitivity interpretation here is flipped compared to the sensitivity interpretation of phi. It's the marginal welfare benefit of slightly increasing available power at a certain site. So we will see these in concrete examples, how they behave And then if we now, so this helps a lot. Thinking of these dual variables in this way helps you very much. We'll see a concrete example of that in a couple of networks in a minute. But it helps your intuition a lot. So maybe the first time you see it, it's kind of exotic, but it's very useful to get accustomed to this idea. And there's a few more things you can say about these dual variables, about their relationships. So this equality here is just this one, sending everything to the right-hand side except for the row. Okay. But now what I'm gonna do is I'm gonna take the psi, which is equal to lambda minus lambda plus, and plug it in here. Okay, I'm just playing around with the KKT conditions. I'm not doing anything too exotic here. And I get this equality constraint here. Which also by default holds for the hub node. So for the hub node, these PTDFs are by definition 0. So also for the hub node, this holds as an equality, but since all of these guys become 0, the row at the hub node is minus the phi. And I'm claiming here that the lambda plus and the lambda minus are complementary. Do you have any intuition about why that's the case, based on what I described here?
Maybe it cannot be full in both directions.
Exactly. If it's hitting the limit at 100, it's a positive flow. It's not going the other direction. The other way around, if it's hitting the limit, this line has a limit, it's 100, whatever the direction of flow is. So it can be hitting it in the up or the down direction. If it's a negative flow, then it can't be a positive one. So I know that for each line here, either one term is contributing or the other. And there is an interpretation here of why this equality holds. So remember when what I mentioned earlier is that, so suppose that this is the hub node over here, node 2. The dual interpretation of rho for bus 1 is how much increase in welfare do you get if I give you an extra unit of power in bus 1. That's the dual, it's the sensitivity definition of what rho 1 is. Well, I could do two things with, if you give me free power at node 1, I could do two things with it. I can either consume it here, and rho 1 will give me exactly how much increased benefit I get from that. Or I can ship it for consumption to the hub node. If I ship it to for consumption to the hub node, the benefit, so now there's a plus 1 megawatt showing up here, and I argued earlier that the marginal benefit of that is minus phi. So again, remember the dual interpretation flips between phi and the rhos. So you can either consume it here or ship it. If you ship it, the benefit is minus phi, and there's also a marginal cost associated with eating up some of the line capacity, and that's captured by these terms here. Because if you try to ship it through, the line may or may not be congested. So if it is congested and you end up eating capacity of the line, these lambda multipliers would tell you how much that hurts your objective function. So that's a way to think about this equality. Now, we're also going to play around with it in a couple of examples. Okay, so here's an example where we get to play around with it. It looks a lot like this example. So we have this 2-bus network, And we have a constant marginal cost at location A, constant marginal cost at location B. Power is cheaper at location A than it is in B, but there is a demand of 100 megawatts at location B. And we're assuming an elastic demand here. So basically this, you can think of the valuation a huge number, or you can think of this as fixed, that we need to satisfy 100 megawatts. So what would you do here if you didn't have a limit on the line? It's a cheaper one, right? So it's an obvious choice to go with A. And I haven't given you any limits on the production capacity of unit A. I haven't, so you can think of the capital P of A being plus infinity. So what you can say, since PA is going to produce, so you can eyeball the optimal solution, right? You don't need to solve it in a fancy math programming software. And you can immediately see that it's, so this is little p, and this is big P. You can immediately see that generator A is producing strictly within its operating region, since its upper production limit is infinity. And if you remember from the KKT conditions we analyzed earlier, that automatically means that the rho for location A is the marginal fuel of generator A. Sorry, the marginal cost of generator A. So you know what the marginal cost of generator A is, you know what the rho for that location is. That just comes out of the KKT condition. But since there really is no capacity limit in this line, basically you can think of this network as just a single thing. Basically buses A and B are indistinguishable. So that means that whatever this is has to be the same as the rho in location B. Now I'm going to complicate things a bit. I'm going to now tell you that the transmission limit on the line is not infinite. So there really actually is a line now in the network. Basically, what I'm going to do is, if I tell you that there is no capacity limit on the line, you might as well think of this network as something like this. It's the same thing, right? If there is no capacity on the line, the line doesn't exist. But now I'm going to introduce a limit of 100 megawatts. So if I introduce a limit of 100 megawatts, does anything change with respect to the primal solution? It's the same one. Can you say something about the rho in location A? Can you say something about the rho in location A? You're starting to think in terms of sensitivity, which is great. Give it a minute. The simplest first thing we saw about the KKT conditions, what was this observation here? If a generator is producing strictly within its operating region, so what is rho A? Come again? 50. Yeah? Cool. Okay. So rho A is 50. Okay, how about rho B? Can we say anything about rho B? We had these three cases. Generator is at 0, strictly within operating region, or at maximum limit. And we said that if the rho threshold, so how much is generator B producing? 0. So when would that happen? If you remember what the rho B needs to be for that to happen. It's at least as much as the fuel cost. Exactly. So rho B is at least 60. That much we know already. Okay. Now, I will tell you also that bus yes, I will now arbitrarily choose this guy, bus A, as a hub node. What is the power transfer distribution factor from bus B on line AB? And remember, the physical interpretation of this thing is how much power will flow on this line if I ship 1 unit of power from bus B to the hub. And I just told you that A is the hub. Here the topology is quite simple, so you should be able to see what the F is. And pay attention to the fact that this is now a directed arc. So line AB means that how much power will flow in this direction when I'm shipping 1 megawatt of power from bus B to the hub? Minus 1. Okay. Some more torture for you with the interrogations. So now let's start thinking of sensitivities a bit. Okay, the first thing. Yes, this is a typo. Sorry, no, this is... Yeah, I think this is a typo over here. I think, and let's just see it here together now, I believe that there should be... Oh, no, pardon. No, these are all correct. Excuse me. Okay, no, these are all correct. Now let's start thinking in terms of sensitivity a bit. What happens in this example if I go from 100 megawatts to 101? Will you change anything the way you're dispatching generators? You're going to do the same thing. It's the best thing to do. So, so you could, but now remember, sensitivity of dual multipliers is the change in the objective function with respect to the change in the decision variable. With respect to the change in the right-hand side. But I can make the right-hand side slightly bigger and see how this changes, or slightly smaller. Both are applicable definitions of sensitivity. So on the one direction, if I make this change in the right-hand side positive, well, if I'm not going to change my dispatch when I'm going from 100 megawatts to 101, the welfare, the objective function is the same. So this is 0. So one valid value for lambda plus is 0. But now I can see it the other way around. What happens if I decrease the capacity of the line from 100 and go down to 99? How are you going to deal with that? So how much is going to be the change in the objective function? What are you going to, what's your motivation for 50? What are you thinking?
50 times
1. But where does the 50 come from? So if I take you from 100 to 99, how are you going to deal with it?
But we have to satisfy 100 megawatts.
Yes, you need to satisfy 100 megawatts here.
Plus 10, 60 minus.
Yes. You dispatch 1 megawatt from the local generator, which is more expensive, and you back this guy off by 1. Okay, so it's plus 10. So that's another valid value for the lambda plus. Depending on how one interprets sensitivity, both are valid. Is it good, Caitlin? Finally nailed it. It's Caitlin, right? Okay, or maybe my French pronunciation is terrible, but in case. Okay, so it's 10. And finally, to wrap things up, let's say something more concrete about the row B. So coming now to this equation here, the generic one. First of all, rho of hub is minus phi, so hub in our case is bus A, and then rho of B is minus phi, the same, but a bunch of other stuff too. It's plus the PTTFs, so there's only one line, so these sums are only over one line. Well, the lambda minus is basically 0. Since the lambda plus is positive, the lambda minus has to be 0. We argued that earlier. So we're only going to pay attention on this term here. The PTTF for this line is minus 1, so the minus with a minus becomes a plus, and we're left with this lambda k plus. Clear? So we have these two quantities. Basically, all this is saying is that rho B is rho A plus lambda AB plus. So we just showed that lambda AB plus is something between 0, when we interpret this as adding a megawatt, or 10. So what can you therefore say about rho B finally? Do we know how much this is? Right? How about this? Something with, yeah, it's a non-negative thing that sits between 0 and 10. So we know that this guy, we already showed earlier that it's no more than 60 because the generator at location B is not producing. But now we also said something more. It's actually something between 50 and 60. Okay. So these are valid dual multipliers for the optimal solution. So all this exercise was, the point was to kind of get you used to, warmed up to the relationships, the duality relationships, as well as the sensitivity interpretations. We're going to see a few more of these things in a minute. Okay. Okay, finally, if I bump up the yes?
So the conclusion is that we can have several values for
Absolutely. The same way that you can have multiple optimal solutions for a primal problem, generally, that same way you can have multiple, because the dual of this problem is also just a linear program. That creates problems in practice, by the way. This is a real problem in markets. The guys, how do you think, and this all depends on, how simple, the simplex algorithm, if it's going to be 50 or 60, it depends on where the simplex algorithm is going to land in some extreme point. How do you think these guys will feel, these loads over here will feel if the simplex algorithm lands on 60? It's an equity, it's an issue in real markets. The fact that you have multiple prices that clear the market means these guys might end up paying $10 more. But all of these are market clearing prices, so they're not going to like it, but they're still going to buy the power. So that's a good point. It's a real practical issue. In fact, in the homework, I'm going to ask you to prove that any price between 50 and 60 does the job. So that's coming up as one of the only 3 questions of the homework. Okay. Now, if I bump up the power demand to 110, then things become obvious, hopefully, again. Now I really need to use generator B. I don't have any more power to take over the line. So both A and B are producing strictly within their technical limits. So the rows are equal to their marginal costs. The row at A is exactly 50, the row at B is exactly 60. Nothing less, nothing more. Okay? Okay, that said, I'm also going to cover the alternative formulation of the OPF, and then we can take a break. So, why am I even going to take time covering this? Well, before I say that, let me tell you that this alternative formulation we're going to see now is the second version of the power flow equations that we saw last week. If you remember last week, we saw one model of the power flow equations with the PTDFs, where we were basically mapping production at buses to flows on lines using PTDFs, these FKNs. The alternative version we saw was mapping production at buses to bus angles at buses. Same exact thing in terms of physics. And here we were using these reactances. So I can write the OPF model either using this or this. It's the same physical model. It describes the same engineering system, but it makes a huge difference in terms of designing a market behind it, because the KKT conditions we get here are used for designing markets and products for transmission, and depending on the KKT conditions, you create different basically different products for different markets. So there's huge debates in the industry about whether we should set up a market for line flows, transmission rights, or for nodal injections, and that has huge practical consequences in terms of various performance metrics of markets. But in any case, whenever market designers come up and propose that this is how we should maybe set up a market for transmission rights over lines, they have to be inspired by the KKT conditions that basically give you the architecture, the blueprint of a market. This is kind of abstract the way I'm describing it now, but hopefully by the end of the course it'll be more clear. In any case, you can think of it in a simplistic way as the physics of the network are what they are. It's how the laws of Kirchhoff behave, but when we take the dual problem, that gives us a blueprint of how to design a market. And different primal formulations give you different dual problems, so they give you different market designs, different market products for trading transmission. That's the bottom. And there's huge debates on which dual problem we should be using. Okay, the other reason for taking a look at this model is that we can actually model changes in the topology of the network. So if this line fails, we can model that using the reactances, because the reactance jumps from something positive to infinity, whereas if we're using PTDF and a certain line gets lost in the network, all the PTDFs change. So this model is also used for modeling changes in topology in the network. So what does the model look like? It's very similar to what we saw earlier. What we change is the power balance constraints and the flow definitions. So the power balance constraints are saying that consumption at a certain location. This notation here is just saying the following. Find all the edges for me in the network that are pointing from the current bus outwards. So for this summation here is scanning over the network to find edges that look like this. That's the summation here. Because the front bus is N and pointing to any other bus. So basically demand plus power flowing out of the bus has to equal production at that bus plus flow of power into the bus. This is another way of describing the energy balance constraint. So in the earlier model we had sum of injections is 0, a single equation. Here we have a bunch of equality constraints using this model here. Now, the other thing that's changed is the definition of flow over line. So now we're working with bus angles, and if you remember, we derived this equality in the last lecture, that the flow of power over line is the bus angle difference between the two buses it's connecting multiplied by this inverse of the reactance. That's all that's changed. It's the same physical model, but it has different dual multipliers. So I'm not going to write them all out. I'm just going to write the ones that are different now. We have the different primal relationships here, and we have these two new different stationarity conditions. So if you think of the sensitivity, the rho that we saw earlier in the first model has the same sensitivity interpretation in this model. And for example, if you look at the if I didn't write them here, but all of these parts of the KKT conditions, all of this stuff over here is identical. So the rho is the same thing as what we saw in the first model. It's just that what has changed is these two equalities, and I mean the primal constraints as well. But basically these two dual equalities have changed. Right, okay, and this is the last slide before the break. And if we do again these this manipulation of the dual equality, so these two conditions here, well, we don't even need to do any fancy manipulation here. All we're going to do is take these rows on the other side of the equality, and we're going to get this relationship here. This relationship is giving you kind of like if you look at it in terms of sensitivity, it makes plenty of sense. So, like I said earlier, the rho at bus n is the marginal benefit of injecting power at bus n. Rho at bus m is the marginal benefit of injecting power at bus m. So if and lambda plus is the marginal benefit of increasing the capacity over a line. What this relationship is indicating is that if a certain line has a lambda which is positive, sorry, this line will be directed from m to n. If the lambda of this line is positive, then that tends to make this difference positive. It doesn't necessarily make it positive, but it helps it from the first term here. This gamma might cancel that out, but there's a bias already from the lambda plus here. So it's often, but not necessarily always, the case that when the lambda that brings, when the lambda of a line that brings power from a certain bus to another bus is positive, there's a bias that the marginal value of power at this location is higher. The rho is higher. That makes a lot of sense. And when you're optimally dispatching a system, you tend to overload the lines that are bringing power to the location where the power is most valuable. How valuable the power is at a certain location is captured by these rhos. So this is a way to interpret this dual condition in terms of sensitivity. But we will see a counterexample where this doesn't necessarily occur, but there is a bias here. Moving on to the market-based material, and I'm going to start by describing to you an example that Bill Hogan used in his 1992 paper, which basically created the foundation for financial markets for transmission as we know them today in most of the world. The paper has been extremely influential, and it was trying to address the following problem. Again, the motivation here is we're moving now away from having a system operator do all of this, solving all of the OPF, because it's difficult for a system operator to have everybody's information. Instead, we want to have each other trade electricity and self-organize an efficient exchange of power. Well, the problem when you start doing that and you have it was easy in the economic dispatch problem in a way. It's more complicated now, because now if I want to trade with someone in France and I'm going to physically inject power to send it to that consumer in France, that power is not going to go through a path that I decide to send it to. It's not like I'm shipping oranges and I choose to take my truck through this highway. The power will go everywhere. It's the same problem that's going on now with renewable energy injection in Germany that is screwing over the Polish operator. Because all of the power fluctuations that are going on in the control room in Germany are then entering, some of them are entering the Polish control area, and they're basically screwing up the balancing of another country. So you have to, this effect as a physical phenomenon is called loop flows. It's a result of Kirchhoff's laws, as we saw. And the way people thought of dealing with it in the early days of setting up electricity markets was by ignoring it, as if it did not occur, and continue trading power as if there were no loop flows. And ignoring it sometimes is a good idea. In this, you know, if a problem isn't much of a big deal and you just ignore it when you're designing markets, maybe it's not the end of the world. But in the case of loop flows, it is an enormous issue. And setting up markets where you ignore loop flows is a guaranteed fail. So the heart of the problem, which is described by Hogan, can be illustrated in this 3-node network that is used in his paper. you have generators in these two buses here and the load in a third location. So if you want to ignore loop flows and think instead of as if you were able to designate from where the power goes to where the power goes, you could set up a market like this. You could say, you know what, forget all this Kirchhoff business. I'm just going to define we now need to respect flows, so trade has to be limited in some way, but let's not make things too complicated. We'll just define a contract path, a bunch of transmission rights, that when you buy them, you can ship power from the generation area to the load area. So now we're not only going to be exchanging energy, but if I want to sell to you, and you are sitting in this different area, you can think of it, for example, as a different country, I will have to also present a right, a piece of paper that entitles me to send 1 megawatt from my generation area to the load, so that the trade can go through. Otherwise, the trade, if I don't present this right, this transmission right, this trade will not be accepted by the market operator. Why we define these rights? In order not to burn these lines. But it's a very simplistic way of defining a transmission right from this production area to this consumption area. So let's ignore for a moment these loop flows and think of defining rights from this area to this area. Well, the question immediately becomes how many rights we should define. Physically, and let's think of this as the hub node. When I'm shipping power to the hub node, in terms of real physics of what's going to happen, and let's assume in this network here that only this line is a problematic line. Only this one has a limit of 600 megawatts in how much power it can carry. When I'm shipping 1 megawatt from 2 to 3, how much of it goes through this line? It's a symmetric network, so all the reactances are the same. Right. If you remember from last lecture, because this is twice as long electrically a path, only a third of the power will go through the difficult path. The other 2/3 will go from the easy path. And when I'm shipping 1 megawatt from here to the load, it's going to be 2/3, and the other 1/3 will go from the other side. And now let's think of, we ignore this and we just think of defining rights from the generator area to the load area. Well, the engineers are going to come up to the market designer and tell him, you know what, if you define rights more than 900 megawatts, we are screwed, because if this player here buys all the, that's exactly what the engineers are going to say. If you define rights more than 900 megawatts, like say 1,000 megawatts of rights, there's nothing in this market to prevent these guys. For example, if they're the cheapest ones and the most eager ones to sell power, they might end up buying all these rights. What's going to happen if they buy 1,000 megawatts of rights? They're going to inject the power, and what's the maximum that these guys could be producing if these guys aren't producing? Even if these are, they're also contributing to the problem. What's the maximum that these guys can produce in bus A? 900. If you give them more than 900, there's this 900 megawatts of rights floating around the market. If it happens that these generators buy them, we have a problem with the actual line. The market might be great, but the line will burn. So the engineers are going to walk up to the market designer and say, there is no way you can give out more than 900 megawatts of lines. But then the economists are going to walk up and say, well, yeah, but that's inefficient for the trade, because if these guys are cheaper than these guys, then you could have shipped how much? If only they were producing. 1,800, exactly. And if it turns out that these guys are cheaper, you are only issuing 900 megawatts of rights, you're limiting the trading volume of the market and you're making it inefficient. Cheap guys that could have entered and be dispatched here, you're keeping them out of the market. Why? Because they couldn't get their hands on only 900 megawatts of transmission rights. So either way, nobody wins. You either risk burning the line or you will inefficiently limit trade by setting up a market that is based on this contract path from generation area to demand area. The problem isn't neither with engineers nor with the economists. They're both right. The problem is with how you decided to define your right to transmit in the network. It's too simple of a definition, this contract path from this area to this area. You have to come up with a more sophisticated product. Okay, I will skip this. Yeah, I mean, I'll skip the slide since we have quite a bit of material to cover. But basically, loop flows in terms of economic terminology are externalities. If you don't price them, they will not send the right incentives to the people that are causing them. And now, let's, okay, so that was an example to motivate why we need markets for transmission. And what I'm going to do in the rest of the lecture is show you two types of markets for transmission. There is a whole family of market designs for transmission, and there are enormous debates. There were, when they were first being designed, there were also enormous failures. So one of the big reasons why California went bankrupt, the California market went bankrupt in 2001 was because of a badly designed transmission market that Enron gained in a fairly, well, there were very complex things that they did as well, but the deck game that we'll cover later in the class is a very simple idea. So there's many ways you can do this. Many of them can be very wrong. I will show you two setups here and some tools for analyzing these different market designs. Okay, so one, the first example is basically based on Stoff's book, and it's the simplest possible setup you could have. And it's here the goal of this example is to show you that a market will do the job. It will reproduce the same outcome as if you were solving the optimal power flow problem centrally. It's the same example as the economic dispatch problem of showing that agents trading reproduce the result of the economic dispatch problem. It's just that now we also have a line here. So let's suppose that we have now deregulated this system. We have two buses, one remote bus with cheap generators and a bit of demand, one city bus with expensive local generation and a lot of demand. So here are the marginal cost functions. The generators in the cheap area start from $20 per megawatt hour and go up at the same rate as the generators in area B, but the generators in area B start from $40 per megawatt hour. And there's the limit on this line of 500 megawatts. Here, the goal of this example is to just give you the idea of the tools that you use for analyzing, for basically coming up with a competitive price. If you remember from the economic dispatch example, there was one competitive price, and it was basically the one that was used to clear also your auction exercise. And I show you how you could compute it. So the idea is here is to give you the computational tools for coming up with a competitive price and a competitive allocation. But before doing that, let's think intuitively first of how this market would work and argue why that's going to be the outcome. So we define here transmission rights from area A to area B. There's no loop flows here, so the definition of the rights is very simple, and there would be no one who would argue against this. So we, except for trading energy, we now also have to present a transmission right to ship power from A to B. So when I'm a supplier at a certain location, I can either sell to the local consumers, or if I want, I can go to the other market and sell to them. But if I do that, I have to present 1 megawatt of transmission right for every megawatt that I'm selling to the consumer. Either I, the supplier, have to present it, or the consumer has to buy one. And then we can do a bilateral trade. But this is how the rules of the market are. We can't just pair up like we did like we would have done in a bilateral market, where I just find Caitlin and I'm gonna make her an offer, she likes my offer, we agree, we go to the operator, say we're trading that much, end of story. No, if Caitlin is at a different bus than I am, one of us has to buy rights also to send power from me to Caitlin. So that's how this bilateral market works. So you can say something, if you remember back from the economic dispatch chapter, we defined competitive markets as economic systems where two things were going on. First of all, each agent was doing the best they could in terms of quantities. So given the prices they were facing, they were price takers and they were optimizing quantities of production or consumption given those prices, assuming they could not influence those prices. But the other important thing in the definition of a competitive market was that there were no profitable opportunities for trade. That's when you get a competitive equilibrium. If you give me prices and quantities of trade such that no one wants to switch and move away, then yes, this is with a stamp a competitive equilibrium. The moment I impose this condition of no profitable opportunities for trade, immediately that tells you a lot about what these transmission rights need to be. Think of what would happen if the price at location B were bigger than the price at location A plus the price you have to pay for a transmission right from A to B. Someone in this economy would really want to move. Can you think of who it would be? If prices at B were higher than price of A plus moving power from A to B. Someone would not be very happy about this and would find an opportunity to find another trading partner and do something better. Who would be unhappy with this arrangement? What do you do if you want to buy jeans in Brussels and they're pricing them at $230 or a euro? In Charleroi. Come again?
You buy jeans somewhere else.
Right, you drive to Charleroi, you pay the gasoline, but at least you buy them at a reasonable price of, I don't know, 60 euro. So if the price here is higher than buying the rights to bring it in from a cheaper place, the consumers here are going to shift away to trading partners in the other area. This argument goes the other way around too. So from that, using this competitive argument, we can say that the prices at B can't be more than the prices at A plus the price of transmission from A to B. The other way around, if the prices at B are lower than the prices from A plus shipping them, then these some of the consumers here that are already buying power from the remote area will shift to more cheap suppliers at location B. So you can argue in these intuitive terms about competitive outcomes, and ultimately what leads to unique outcomes is this argument that there is no opportunity for, no one wants to move. The moment you impose this condition of market clearing, that no profitable opportunities for trade, that immediately leads competitive outcomes to, if not unique, very restricted sets of allocations and prices. But that's, you can make that argument in an intuitive basis, but one of the goals of the course is to teach you how to do it using KKT conditions, basically. So let's think of formalizing this verbal argument that I gave to you in terms of KKT conditions. And we can just formalize it by looking at the problem of importing power or buying it locally from the point of view of consumers at location B. So this is the problem that the consumers are facing. Do you agree with this formulation? dA here represents how much power I'm importing from the remote area, and the capital DB is how much I am going to consume at my bus. Does this formulation make sense to you? So what is the objective function saying? What is this term here?
So what is capital D?
Capital D with subscript B is the fixed. We're assuming that the demand here is fixed, it's inelastic. We have to come up with 800 megawatts from somewhere. Capital D is the 800 megawatts. Little dA is how much power I'm bringing from outside. So what is the objective function saying? You can do two things.
So dB minus dA is what B produces.
Is what bought locally, exactly, and little dA is what I'm importing from outside. Well, if I'm buying locally, I'm paying local price rho B. If I want to import from outside, I'm going to buy at the outside price, but also pay for the transmission rights. How much am I going to bring from outside? It's exactly little dA. Okay, so no need to introduce a new transmission variable. In more complicated models with loops, you need to, but not here. And this is just saying that I don't need to buy more than my total demand. There is no benefit in this problem because demand is inelastic. So you just need to meet capital D subscript B. Okay, you take the KKT conditions of this problem the same way we've seen in previous lectures. And what you can say is the following. So, first of all, you know that if this market is going to have a competitive outcome, and there is no way that, well, let me ask you this. Is there any way that the line might not be at its full capacity in this market? Who's the cheapest? Who's the first to jump in and trade power in this system? Who's most eager to sell? A. The first slice is in A. The first little customers in A, are the cheapest. They can produce at 20. They're going to start selling. We're going to be moving up their supply curve. At some point, first of all, they need to satisfy local demand. If it weren't for this damn transmission constraint, they would jump in the market of the city and take all over it. Why? Because if they are producing 100 here for the market here and another 800 for the other market, they're producing a total of 900. That can be produced by the guy that is selling at 20 plus 900 divided by 50, that comes out to be 38. Not quite. 38, right? Yes. So even that guy that's going to produce the 900th megawatt is still cheaper than these guys who are starting their offers from 40. So if it were up to the suppliers in A, they would all take over the market in B. The problem is that you have the transmission constraint, but the sure thing is in a competitive market, the line will be loaded to its limit. Why? Because it can only carry 500. So they can't go above that. So they're going to max out the limit of the line, but if you look at the KKT conditions of the supplier, you know that his DA will be positive. He will be bringing power from outside. That means that this is activated as an equality constraint, but you also know that he cannot satisfy more than his demand because the line cannot carry more than that. So also here, this will be a strict inequality and the nu will be 0. So that means that basically the mu goes away here. This is an equality. So this argument I made earlier on intuitive terms, you can derive it from the KKT conditions of the competitive market. That the price of the transmission rights is the price at the expensive area. Mine is exactly equal to the price at the expensive area minus the price at the cheap area. You can derive that formula. So using these tools is something I would really like you to learn how to do in a systematic way in the course. Okay, the bottom line is that if you go through the analysis, what you're going to end up having is that generators at A will produce, first, they will max out their production, 600, 100 for the local demand, 500 that's been carried over the line. Then the rest, the cheapest of the generators in B will be activated and produce up to 300. The prices at A will be right, okay, so yeah, the prices at A will be the marginal cost of the 600th megawatt, because that's the most expensive guy, so that comes up to $30. And the prices at B will be the 300th megawatt of the cheapest guy in location B. You see where these numbers are coming from. I'm just plugging the production at location A to this marginal cost here. So 20 plus 600 divided by 50 is 30. 40 plus 300 divided by 50 is 46. The difference is the price of the transmission rights, the price at which these rights will be traded in a competitive market. And we've basically solved the competitive market problem. It looks a lot like what you would get from solving a different problem though, right? What problem is that? What would happen if the system operator decided everything and there weren't any markets in the first place? The system operator owned all the generation and needed to satisfy 800 in the city, 100 in it. Exactly the same. So I spent the last 10 to 15 minutes trying to justify to you why a market where we're making bilateral agreements would reproduce exactly the same outcome as if the system operator knew everything. It's arguing this in a more complicated network is more complex, of course, but the intuition is the same. Quantity adjustment of price-taking agents and no opportunities for profitable trade, which is basically complementary conditions of market clearing. These two things, once you learn how to master them and formalize them in your head, you can compute competitive outcomes, and then you can prove that this KKT system is equivalent to centralized optimization. So the two things will produce the same allocation. Okay, now, that is an argument of why you can get away with setting up a market, even if you have transmission constraints, by defining transmission rights. There was an alternative idea that was really clever and was originally proposed by Fred Schweppe, who was a notorious professor in MIT, did a lot of work in power engineering, and then started thinking of the optimization interpretations of power engineering models. And he wrote a book along with Karamanis, who was actually the president of he's a Greek. He was also the president of the Greek Regulatory Authority for Energy a few years back, and he's now a professor at Boston University. Schweppe died quite a few years ago. Karamanis is still very active, and Tabor and Bon, as far as I can remember, are consultants in the Boston area. So these guys were like a dream team of electricity market design. And about, how much? 25 years ago, they wrote this book called The Spot Pricing of Electricity, where they came up with a really clever alternative to defining transmission rights. And the idea at the time was perceived as too complicated to implement in real life. I'll show you the reason why it was perceived as such. But a few years later, most of the markets in the US adopted the idea. It's a very robust idea to set up a market and deal with transmission at the same time. And it seems like it's probably the best way you can structure an electricity market without, you can bring more complicated layers around it, but the heart of the market really has to rely on this idea of locational marginal pricing. What was their idea? So they said, you know what, forget about transmission rights. Let's just set up an auction, kind of like the same way we did 2 weeks ago for your homework. And are you ready for my amazing idea? We're gonna do the same thing as 2 weeks ago. It's just that now I'm gonna solve an OPF as a system operator. And I'm just gonna take that row n from the problem. So the rest of the auction is the same from your point of view as market participants. Loads submit what price quantity pairs, decreasing. Suppliers submit price quantity pairs, increasing. I, the system operator, take them in. Now I don't solve an economic dispatch problem anymore. I solve a more complicated problem, which is the optimal power flow problem. But that's okay, because I know the limits on lines. That's part of a system operator's existence, is to take care of the transmission network. It's what they do every day. They know the flows, they know the limits of the lines, they know the PTDFs of all the lines. You have like armies of engineers spending time paying attention at these things and making sure they don't burn. So all we're saying now is we are going to collect information from everybody, solve the optimal power flow problem, and the price that we're going to use for trading is not going to be that system lambda that we saw in the economic dispatch problem. It's not going to be this rho. But what is different now? How is rho different from that system lambda that we saw 2 weeks ago?
It's different for every.
Right. That's why their idea was perceived as too difficult to implement in practice. In a real system, you have thousands of locations. So the idea of trading, like running basically thousands of auctions at the same time, was perceived as academics proposing crazy stuff. Never gonna happen. Other than that, the rules of the auction are identical. If the row is, if you're in the money with respect to the row, you supply if you're a supplier. If you're out of the money, and when you supply, you get paid the row. If you're out of the money, you don't produce anything and you don't get paid nothing. As a consumer, if you are asking for more than rho, you get it, but you pay rho. If you're below, if you're out of the money, you don't get anything, you don't pay anything. The rest of the rules are the same. Now, 13 minutes. Okay, we can do a bit more. Okay, yeah. Okay, so why is this a good idea? Let's formalize why the idea was a good one. Let's look at the optimization, the profit maximization problem of generators. It's this. But now I've changed the rules of the auction. The rho it's not the system lambda anymore, it's the locational rho. Other than that, the optimization problem of the generator is identical, as are the KKT conditions. We've already seen these before in economic dispatch. Same for loads. They are paying rho, a locational rho, which is the rho of the auction. So this is the KKT system of the loads. From the point of view of the system operator, now I'm gonna, because we're submitting block bids, I'm not gonna have gradients anymore. I'm just gonna have fixed the blocks that you're submitting. So C for suppliers, V for consumers. What the system operator is gonna do is it's gonna collect all these block bids, solve the OPF, the optimal power flow problem. A subset of the conditions of the OPF that we saw in slide 4, I think, of today's lecture was this set of conditions. So these conditions also show up here. And basically, if I select this rho star to be the same that the optimal power flow problem gives me, I know the optimal power flow problem with this special rho is going to reproduce an optimal allocation of production and consumption. So if this is the signal I send to the suppliers and consumers, they're going to respond to it with an optimal level of production. This is why you need to send this as the market clearing signal. It's replicated in the optimization problems of the generators and the loads. All you need to do is collect their information. As long as they bid truthfully, and as long as you send this as the market clearing signal, your KKT conditions are the same as their KKT conditions, provided this rho star is the one you send them is the one that you get from your OPF problem. Okay, so that was the idea. Now, what have we done here, basically? Did I ever even talk about transmission rights in this setup? They don't exist, they don't have to. That's the cool thing about this idea, is you don't have to even define transmission rights. You just have everybody sell at their market, their local market. You don't give them the option of selling outside, but you make sure the price you pay them is the proper price. But it simplifies extremely operations, because the control room continues doing everything the same way they used to. All they need to do is now collect these bids. So the idea is looking very promising. The only concern was that, okay, now we have what, 1,000 different auctions running at the same time, plus we run this auction every 5 minutes, because that's how optimal power flows are done. They're resolved every 5 minutes, depending on how demand and supply evolve. So, proposing this as a market design for enormous engineering systems was considered ridiculously complex, but it's happening. So this is the biggest market worldwide. It's the Pennsylvania, Jersey, Maryland system. I was taking these pictures as I was preparing your lecture notes on Saturday. So it's a time shift, so I wasn't up at 5:40 in the morning to prepare your notes. The color charts are, first of all, we're talking about a big chunk of the northeastern United States. The color charts are, the purple here is something between -1,000 to -$10 per megawatt hour. So you're getting paid to produce, and we will see why that could happen. And the largest prices are the red and everything. You know, the blue is kind of cheap. The yellow is a bit more expensive, and as it's becoming orange and red, it's going up, and it's going, I think, up to $400 per megawatt or $1,000 per megawatt hour. In the morning, not much demand, low prices, kind of uniform across the whole area. This is updated every 5 minutes. Then it's 8:40 in the morning. Minnesota, I think here is getting, no, it's maybe not Minnesota, it's maybe not part of PJM anyway, some place here with, this is probably a lot of wind that is being produced here by the lake, and it's being taken in, it's collapsing the market price, and in fact the price is going negative here because some fuel generators are willing to pay money to stay online because they don't want to shut down and then take startup costs again later in the day. So these are generators that are bidding negative to stay in the market to avoid startup costs later in the day. And you have negative prices in this area. Then later in the day, New York and New Jersey over here are waking up, so you have to send power into New York. There are lines that are bringing power into New York that are congested, so the local power in New York is jumping up. The power, the LMP outside of New York is less expensive, and so on. Here, probably again, you have some local overproduction, probably again due to wind, that is causing small or negative LMPs in this hole over here later in the day. But the takeaway is that this, and these are hundreds if not thousands of prices that you're seeing here. This colored diagram is based on a lot of data. So this is happening. It's happening in the largest markets worldwide, and it's happening as it was envisioned. So let's try and let's spend the next 7 minutes trying to understand a bit how these prices behave. And again, these notes are based on Corey's class notes. He's a colleague at Arizona State University. So Corey made up this cool example where you have 3 generators, cheap one in A, not as cheap in B, expensive one in C. So $50, $70, and $100 per megawatt hour. The network is, as usual, symmetric. No demand in A, a bit of demand in B, and 100 megawatts of demand in C. So let's see how these LMPs can behave and how we actually can derive them. First example we're going to see is all the lines have the same limit, 25 megawatts. And a very useful exercise to understand LMPs and loop flows is to identify why the optimal solution is what it is. I claim that the optimal solution is generator A should produce 25 megawatts, generator B should produce 75, generator C should produce 50. If there were no transmission constraints, what would you do here? You want to take as much as you can from A. If you can't, why? Because only 25 megawatts can go up, you will bring in B. Now, if both of them are producing and hitting the limits of these lines, finally you need to bring in C. So C is a solution of last resort if the lines are already at their limits, which they are in this specific example. I argue they are because I'm going to make a proof to you that is going to use local optimality as the argument, but because this is an LP, local optimality basically implies global optimality. So, okay, you don't like my solution. What do you suggest we do instead? Let's move generator up a bit. Sorry, let's move generator down a bit if you don't like generator A down a bit if you don't like the level at which generator A is producing. Is there any chance that's going to be a good idea?
No, because
it's the cheapest one in the network. There's no chance. So get out of here. You're wasting my time. I don't even want to hear about this idea. What do you suggest instead? Well, how about we move generator A up a megawatt? Okay, your idea sounds very promising. Let's see what will happen. Well, tough luck. It's already giving the line here a hard time. If it produces an extra megawatt, it will overload the line. If A goes up a megawatt, someone has to back down and make sure none of the lines are fried. Turns out that the cheapest way you can do that reconfiguration is the following. If A goes up 1, which is going to cost 50, this line is going to suffer because he's going to send up power that way, and that line is already overloaded. One way to deal with that, and it turns out it's the most cheap way you can deal with that, is to have an equal amount of power produced by this guy and back this guy down by 2 units to make up for the increase of this guy and the increase of this guy minus the 2. So they're going to both ship power to B, this change, but this guy's flow is going to cancel this guy's flow, so the line will remain intact. Okay, because a third of each megawatt here will go in this direction, a third of each megawatt will go in this direction. If they produce the same, these flows will exactly cancel each other because of the linearity of power flows and so on. So that way, yes, a change of plus 1 megawatt for A is an option, but is it cheaper? So here's how the numbers turn out. You get an extra cost of 50 by moving A up 1. You get an extra cost of 100 by moving C up 1. And you get savings of 2 times 70 by backing down B. It's more expensive. So nice try, but not really. Alternative idea. Well, let's look at 2 easy ones. How about decreasing production in C? I will tell you already that for the present optimal solution, both of these lines are overloaded. There's no way. If you decrease this by 1 megawatt, there is no way you can bring an extra megawatt up. Why? Because you're already using these lines to their limit. Okay, how about if we increase C by 1? You're doing the same thing. You're telling me to dispatch the most expensive generator. Not a good idea, we can discard it. So the only interesting other thing to look at is moving B. And it turns out if we go through the numbers that it's more expensive as well. In fact, there's one case here missing, which is moving up B by 1, sorry. But hopefully you get the idea. So all of these proposed changes, if you also account for flow limits, are more expensive. That's how you can prove optimality of the present solution. Now, in the 1 minute that is left, I want one last takeaway from this slide. Do you remember, if you remember the KKT conditions from the original OPF, remember this is solved now by the system operator. So the KKT conditions we saw for the OPF in the beginning of the lecture, they're the same ones. They haven't changed. So what are the rows going to be here? There was this really simple idea for getting the row fast, if it was satisfied. The really simple condition, if it was satisfied. Sometimes it's not. But when do I know that the rho is equal to the marginal cost of a generator in a certain location? If it's producing strictly within its operating range. I know that the rho at that location is the marginal cost of a generator that is producing strictly above 0, below max capacity. Here there are no max capacities for the units. All of these guys are producing strictly below their max capacity, which is infinite. So rho A is 50, rho B is 70, rho C is 100. Now, here's an example where LMP differences do not mean that the power flows in a certain direction. Rho B is more expensive. It's higher price than rho A. That doesn't mean power is flowing from A to B. So there's a bias It's often the case, but not necessarily so. So that's one takeaway from this slide. So in this case here in particular, the flow between A and B is 0. The fact that there's a positive LMP difference between the lines doesn't mean that power is flowing to the more expensive bus.